I'm Mark Gouker from Lincoln Laboratory, and as I'll describe in a moment, that Lincoln Laboratory is up in Lexington. Of course, we've had a long association with campus, as I'll describe. And we're going to change gears here a little bit and talk about next generation computing. But before I begin, I want to thank Vladimir for inviting us to participate in the Nano Summit. We're very honored to do so. Of course, we've collaborated for decades with researchers on campus, but that has gotten more engagement as Nano has been constructed, and we're looking forward to that. So I do have a couple of colleagues that will dive into some details as we get into the session. So Ryan Keech will come up after I'm done, and he'll talk about our work on ferroelectric FETs. So Ryan has joined the laboratory about 4 years ago. He came to us from Intel, where he was working on the 20A process. He did his education at UConn and Penn State University. And then after that, Alex Wynn will talk about our work in superconducting electronics. So Alex has been at the laboratory about 10 years and focused on superconducting electronics that whole time. And he did his education at Boston University and Vanderbilt. So with that, I'll jump into next generation computing. And so since this is the first time that somebody's from Lincoln Laboratory has talked at the summit, I thought I'd begin with just, in my setup piece, a little overview of who we are at Lincoln, where we came from, and then how we collaborate and connect with Nano before we get into our more detailed technical talk. So the laboratory actually has its origin in the radiation laboratory that was on MIT campus during World War II. You might not realize that microwave radars were invented in World War II with the British. About half, I think 100 or so radars were developed at the Rad Lab. They deployed about half of the radars that went into theater there. At the end of the war, they shut down the radiation laboratory. They wrote a series of books that really defined the foundation for microwave engineering, and that was it. But then in the late 40s, early 50s, the Soviets had developed a nuclear weapon, and we were concerned about them flying a long-range bomber over the North Pole. And so the government came back to MIT and said, hey, you did a great job for us in World War II. Can you build a radar system for us to protect the US? And so we did. It ended up being the SAGE system. It took about 7 years to develop. It was operational from 1962 to 1983. It was deployed well over 100 radar installations with communication networks, et cetera. So today, our mission has grown quite a bit, and we're technology in support of national security, and we have a number of mission areas that are shown on the bottom of the screen there. So as I mentioned, we're out in Lexington, Mass. On Hanscom Air Force Base. We have about 2 million square feet of lab and office space. We're about 4,500 employees, and we did $1.4 billion worth of research last year. And our key roles are really system architecture engineering, so this is like designing constellations of satellites and how they would get used. Long-term technology development, sometimes we engage for decades with some of our sponsors to develop technology. But what we're really passionate about is system prototyping and demonstrations. And this is a great example of that. So we developed or matured a 3D LiDAR system. So this image was collected over Boston, so from an aircraft that flew at 13,000 feet and collected in under 2 minutes. And so what makes this image different from a typical image is that the imager that we use, behind every pixel, it has a timing circuit. So we can send out a pulse of photons from a laser, and knowing the position of the aircraft and the direction that the imager was pointed, we can collect the data back because we have the time of flight information, and we can create this 3D point cloud that we can then traverse through this. And so this was actually deployed for the Department of Defense in Afghanistan and South America, but it's also been used by FEMA for disaster relief after earthquakes and hurricanes and the like. So a lot of the prototype systems that we build actually rely on microelectronics, and so through the years we've developed very capable microelectronics fabrication capability. And we sort of intentionally position ourselves in this no man's land, as I'm showing here. So you can kind of plot research flexibility versus process maturity. And of course, the factories that make CMOS are highly capable, yet they're very adverse to any kind of change in their process. The universities on the other end of the scale, their job is to create new devices, And so they embrace materials diversity and fabrication flexibility. However, they typically don't have the scale to create circuits that are going to go into prototype systems. So we choose to be in this middle land so that we allow a lot of materials flexibility, yet we have quality management services or systems in place so that we can yield larger circuits. So our facility, we operate at 24/5. There's about 60 people that are dedicated to this, and we have proper certifications for that. And so how we connect with Nano is shown here. That, of course, Nano isn't a normal university clean room. It's much beyond that. And part of what's happening is that we're installing 200 millimeter tools. But all the same, that Nano is probably going to be a little more focused on device discovery and materials research on that 200 millimeter platform. And we're working out the process where we can transfer wafers back and forth, where we can take advantage of some of the capability that we have at Lincoln Laboratory to do more routine processing, mature those devices so that we can get them into these prototype systems that we really enjoy building. So we work on a variety of materials, so we're definitely a high mix, low volume fab, but we will work at all stages of materials maturity, from component explorations with emerging FET technology to component capability, both optoelectronics as well as electronics devices, and some prototype systems. So we have full flow processes with PDKs and all of that. And you can get to us through Nano. We're sort of tied at the hip from that respect, and we welcome collaborations going forward. Okay, so with that as a little bit of introduction, let me set up the talks that you'll hear next. And so one of the things that we like to do as we work on research is really try to understand where it fits into the big picture. And so we've created this hierarchical model for computation, and of course our computation systems are extremely complex machines, even though they're micro scale. But if we look at what goes into one of these computational systems, that we see that sort of at the foundation, we decide how we're going to encode the information into a state variable, what kind of device we're going to use, the materials, et cetera. And then as we go up into the stack, we have different levels of optimization, what kind of circuit architecture we're going to use, computer architecture, et cetera. And in the golden era of scaling, the Dennard scaling, that in sort of the 2000 timeframe, that life was great. All the focus was at the lower part of that stack, making significant progress every couple of years with faster processors, more transistors, et cetera. And so there really wasn't a lot of need to optimize the higher end of the stack. What we've seen in the last couple of decades is that as that Dennard scaling has slowed down or stopped, that we have optimized our computer architectures in terms of started with GPUs and then TPUs, and now we have AI processing units and the like. But even so, with those optimizations, we're starting to run out of steam, that we're having to create nuclear power plants to power our data centers for that. So it's our belief that we can, maybe now is the time to start looking at the lower end of that stack a little bit more and see, is there new technology or different technology that we can use to relook at that and reduce the energy consumption of these computational systems. And so what we'll see in Ryan's talk is a different type of CMOS transistor that's based on ferroelectric layer in the gate stack for benefit. And then with Alex's talk on the superconducting electronics, we're actually going to go all the way to the bottom and look at a different state variable in terms of how we encode the information into the circuit, and then the material system will be different. So with that, I'll turn it over to Ryan. Okay.
All right, well, good afternoon. Really appreciate this opportunity to be with you all, and want to thank all the organizers for the invitation. I think it's been a great summit so far, and happy to be part of this next generation compute session. So I'll be sharing some of the technology that we're working on at Lincoln Laboratory to help develop computer chips that will function more akin to how our brain functions. And before I get into that neuromorphic computing and the ferroelectric transistors that we think will enable that, I want to put up this slide as just kind of a broad landscape overview of the computer chip technologies. So this technology has continuous innovation at its core, right? This is the technology of Moore's law, better performance every year to improve our lives in a myriad of ways. And those innovations, they cut across all the system hierarchy of these chips. So starting at the very building block of our integrated circuits at the transistor level, we see the adoption of new materials and new device geometries in order to further the number of transistors that we can fit onto a given size chip. We look at interconnects. Today we're seeing the separation of the power routing from the signal lines in order to improve efficiency of the way these chips operate. Like Mark said, we're seeing the introduction of new chip architectures altogether. So the graphics processing unit that we see has been very popularized from NVIDIA, taking over, giving more computational throughput compared to what we used to rely on, just the standard CPU years ago. We're also seeing innovation in packaging. So adoption of chiplets, 3D heterogeneously integrated materials to advance the functionality of the chips that we put into field. And all of these innovations at the leading edge, these are all going to be leveraged and used to enable the most computationally intensive technology applications that face us today. So from the machine learning algorithms and large language models that go toward personalized AI, pattern and image recognition that would be required to support autonomous vehicles, for example, the drug and material discovery, what proteins should we be synthesizing, all the way to our edge devices, our distributed sensors that need to transmit data to the cloud for computation to be done, and then get some signal back on next instructions to comprise the Internet of Things. And of course, the chips that we design for all of these applications, we want them to work as the highest performance possible. And the way that we get more performance from the chips that we design for those applications is typically bought with power usage. And I think that can be appreciated by just looking at this two-axis plot. The y-axis is computational throughput that these various chips that are populating the graph kind of are capable of delivering. And you see that if you want more performance, you typically get that with more power. And it's a tricky trade-off, especially as we consider that today, somewhere between 5 to 15% of the global energy production is used for computation. And this is forecasted to rise very steeply as we see more data centers come online and the Internet of Things grow faster still. So we need a new paradigm here. We need a better way of getting more performance for a given power. Because the alternative is, as Mark alluded to, you see some companies saying, oh, we'll just make our own nuclear reactors to power our data center. And that might work for some of the centralized technologies, but until we're all ready to sign up to have our own personal nuclear reactor, we need to come up with something more creative on the device side. And so to do that, I think it's instructive to consider this line that defines the performance you get for a given power usage. And this line is defined by the von Neumann bottleneck. This von Neumann bottleneck gets its name from the von Neumann architecture. This is the architecture that leading chips today still use. So if you were to delid the latest Intel chip that's coming out this month, you'll find that there are multiple tiles here. There's a Wi-Fi tile, we have a graphics processing tile up top, some I/O here. But the biggest tile on the chip is the CPU. And what we have here is an 8-core CPU. You see the big cores around the periphery of the CPU. And all around those cores are these different levels of cache memory. And the cache memory is there to give the logic cell that's doing the computation easier access to the data that's stored. And there's level 1 cache that's relatively fairly accessible. But as these technological needs require more and more data to perform their functions, the logic cell needs to reach further and further away physically, because the logic and the memory are physically distinct components, into maybe the third level of cache memory, or the main memory that might be off-chip entirely, costing 100 or 1,000 times more in energy penalty to go get that data to do an operation on. This also accounts for about 80% of the time latency in the way modern chips operate. And so what can we do about this? Well, if the issue is that we have distinct functionalities of our chips located in distinct areas, well, let's just put them closer together. Let's improve the memory capacity in those cache cells. And indeed, this is what's done on those GPUs. So this is why I have the GPU and the supercomputer slightly above my von Neumann bottleneck line, because they're already doing this. They're getting the memory cells closer and closer to logic. They're developing ways to make those level 1 caches larger. But we can do better yet. If we take a cue from nature and think about how our brains operate, well, our brains actually do computation in memory. And so if we could not just put the computation near the memory, but actually enable the memory cell to do computation itself, well, now we're talking about a way to access high throughput, highly efficient chip architectures. And if you want to design this type of in-memory logic cell, there are a few main things you're going to be looking for. One is low read and write energies. Second would be fast read and write times. And the third is non-volatility in the architecture. We don't want to have to always apply power to this circuit in order for it to keep its memory. So we really want the non-volatility as well. And as you consider the spider chart against these variables that would be attractive for an embedded non-volatile memory architecture, this ferroelectric field effect transistor scores quite well across the board. And so what I'd like to do is, we understand the leading edge today, but what's coming tomorrow? I think a very attractive device is the next generation transistor of a ferroelectric transistor, and how this could enable beyond von Neumann architectures, in-memory computation, and potentially neuromorphic compute chips. So I'd really like to introduce this ferroelectric chip for anyone who hasn't heard of it yet. A ferroelectric material, let me start there, is a material that exhibits a spontaneous and reorientable internal polarization. So a standard dielectric or a standard insulator, the center of positive and negative charge on an atomistic unit cell level are co-located. So there's no dipole that exists in a regular insulator, but a ferroelectric, the spatial center of positive and negative charge are physically separate. And so there exists this spontaneous dipole in the unit cell. And the interesting thing about ferroelectrics is not only does a dipole exist, but you can indeed apply an external electric field and switch the orientation, and then that unit cell will stay in that polarization orientation until acted upon. And you can cycle these many, many millions or trillions of times. They're very stable materials. They've been known for over 100 years. However, it's been only observed in material systems that are not CMOS compatible or not very CMOS compatible, either in their composition or their scalability. That was the case until around 2011, where stable ferroelectricity was identified in doped hafnia material systems. So while hafnia is a normal dielectric, if you add some dopant elements, you can actually stabilize ferroelectricity. And so what I'm showing here is hafnia being doped with zirconia, where both end members, hafnia and zirconia, are normal dielectrics. We see multiple stable ferroelectric phases in the intermediary. And this is very enticing now as you start to think about ways to include this spontaneous polarization into computer chips because, well, by the time this was discovered in 2011, hafnia was already the gate oxide for state-of-the-art devices. And so you're already halfway there. If we could just add some zirconia into that compositional mix, we could start playing with this new mechanism at the heart of the transistor right next to the channel operation. And indeed, these different phases of ferroelectricity are useful. I'm going to talk mostly about the in-memory compute capability with the ferroelectric phase, but if you start pairing these together, you can build some very interesting gate stacks where, now I won't have the time today to get into the details, but I encourage you to look at this paper that we worked on with Professor Chima, who's now MIT faculty, where we were able to take our 90 nanometer CMOS node. It's a pretty mature node, but by integrating these hafnia, zirconia, superlattice gate stacks, we were able to demonstrate a 2-node advancement in the transistor performance, competing with a 40 or even a 30 nanometer transistor node. So yeah, please do check out the paper, but I'm going to continue on now with our in-memory compute theme, thinking about how a ferroelectric transistor could be built with this material. First, take a step back. I'm sure a lot of us are familiar with a transistor, but for those who aren't, we're talking about a device it's a 3-terminal device. So if we apply a bias from, if we apply a bias from source to drain, we would be providing a driving force for current to flow through the silicon channel. But because silicon is a semiconductor and kind of ground state, it's not a very good conductor of those electrons that want to flow. So we would register a very low current, think nanoamps. But by applying a very small signal to the gate terminal, that's what I'm plotting on this x-axis, you'll see many order of magnitude increase in the amount of current that's reaching the drain as the channel is inverted and this silicon becomes strongly conducting. So this is the general basis of a transistor. We can use these two distinct states to store data, perform logic operations, and the like. So what happens if we put a ferroelectric right there at the heart of the device as the gate oxide? Well, when a ferroelectric material is initially grown, it will typically organize itself into domains that you'd have offsetting polarization directions. So if you look closely here, I have some domains where the polarization is pointed up and some where they're down, and they kind of go back and forth to kind of find a nice equilibrium without too much charge free energy to pay for. But like I said, if you apply a voltage across a capacitor, like the gate oxide, for example, you can align all of these dipoles such that all of the positive charges would be facing maybe the bottom of this capacitor. As the gate oxide, that means you're putting positive charges right near the channel interface. That attracts negative charges up in from the silicon. And effectively what this does is it reduces the voltage required to be applied to the gate in order to turn the device on. You can remove this voltage and it will stay in this state and function as a normal transistor with this lower threshold voltage. Alternatively, you can switch the polarity of the applied voltage, reorient all of the domains, end up with a positive charge at the bottom, attracting that kind of holes into the channel, and you'll see the turn-on voltage shift to a higher value. And so what we have is this reprogrammable switch where we can put the device in a low VT or a high VT state and define this memory window such that based on however it's programmed, we can later go back and ping this gate with a given read voltage and see if the bit is read at low current or if it's at high current. And this is how this transistor non-volatile memory works. And because of this functionality, it's, again, very attractive for in-memory computation. This is some data from Global Foundries. They have arguably the most mature ferroelectric FET technology. This is not just a concept, even though I've only really shown schematics so far. These devices are being built. They're being built at scale. Global Foundries has pretty high yield and repeatability on these devices. They're using a gate-first integration scheme, and instead of doping the hafnia with zirconia, they're doping with silicon. Nonetheless, they have a nice, impressive memory window, and through this gate-first integration scheme have shown some promising circuits in university collaborations using this device. They've also been ahead of the pack in identifying what are the real challenges to really put this device into high-volume manufacturing. They're working on charge trapping and endurance problems that they've already been able to identify. We're also working on this device at Lincoln Laboratory, and we're taking a slightly different approach. We're using a replacement gate scheme, so this means we fabricate the device nearly till it's about done. You really could call it done and make contact to the device and use it as a transistor. But rather than calling it done, we go back and we open up and remove the gate that was present, the polysilicon that was there that was serving as the dummy gate terminal and the silicon dioxide gate oxide that was there. We clean it all out, and now we have an opportunity to redeposit a special gate oxide, a hafnia zirconia gate oxide, or any other ferroelectric material that's of interest. And once we do this, we can move it right to the end of line, make contacts. There's no more high thermal process steps that might disrupt the functionality of those special layers that were deposited. So with this technology, we're working on developing a full process design kit that has all of the parameters and design rules that would be needed for a circuit designer to come up with the ideas of how to actually use this new device. We haven't before had a transistor that could have its threshold voltage changed like this in a non-volatile way. How do you even use that? We're hoping to be able to set up a mechanism where we can work toward finding the best gate stack possible for this type of technology. And kind of some early looks at what can you even do with this. have already been published in literature. So Professor Kai Ni, who's a collaborator of ours, is showing here on your left some very efficient, highly parallelized memory cells, where you could do this highly parallelized memory using a standard SRAM circuit, but it has a very large footprint and it requires a whole lot of power. But nonetheless, this is the architecture that's used on server chips and alike. But by moving to a ferroelectric FET architecture, you'll see about a 6-order of magnitude improvement in the energy and time latency with a smaller footprint due to the non-volatile nature of the device. Another example here, Professor Bowen at Stanford is thinking about neuromorphic computing and recognizing the spatial temporal electrical patterns that our brain uses in order to encode complex information. And, well, there's a little bit of animation there, but could we use the same type of spatial temporal signature and apply it across a varied gate electrode? And because we have control over how much of the polarization rotates with an applied electric field with the ferroelectric, we can encode a very specific conductance through the channel based on the localized dipoles that are in the ferroelectric. So we have this like secondary axis to start encoding information and mimicking neural networks. So just to summarize, we think about these very computationally intensive applications and want to continue to find ways to enable high performance at lower power, improve efficiency. And we think that the in-memory computation with ferroelectric FETs is a great candidate. We're working on this in the Microelectronics laboratory just up the street, MIT Lincoln Laboratory, to support further lab-to-fab transitions. Talked about the leading edge and how ferroelectric transistors could play into neuromorphic architectures in the future. But the exciting thing is that there are a whole host of potential solutions to advance the technology of computer chips. And my colleague Alex is going to come up here shortly and speak about superconducting electronics as one of them. With that, I'll just thank you for your attention and leave this here for a second, just thanking the collaborators from MIT, UC Berkeley, Notre Dame, and the whole entire microelectronics team. So thank you very much.
I'm Alex Wynn. I also work at Lincoln Laboratory. I work on an even more exotic technology than ferroelectric transistors, although it's actually been around a little bit longer, and so in some ways it's more mature and we're building bigger circuits out of it. So I'd like to tell you a little bit about that. So a little bit of the background, why bother with such an exotic technology? We're going to replace semiconductors with superconductors. People have thought this might be a good idea for quite a while. As a quick refresher, semiconductors are terrible at conducting electricity. You can make them a little bit better or a little bit worse. Normal metals are pretty good conductors, but they still burn a bunch of power and you have Joule heating. Superconductors at DC don't burn any power, so you could set a little circulating current in the superconductor and it will sit there until the end of the universe. So that might be a low power way to build electronics, but how are you going to practically do that? So there's a bunch of potential applications. I'm going to focus on digital electronics, which is sort of the same theme as my colleague. There's also applications for things like RF electronics, particle detectors, and quantum information science. Superconducting qubits are sort of the leading quantum modality. Particle detectors can be made all sorts of ways. Superconductors have this quick turn on that depends on temperature. So when a particle hits it, you can get good energy resolution by seeing how good of a superconductor it is right at the transition temperature. And similarly in the RF domain, there's very low losses at high frequencies. Okay, so you know a little bit about this. Energy of computation is becoming enormous. People are building multiple nuclear power plants to deal with it. Moore's law is over, Dennard scaling is over, and so we might try to do something different. So I'm going to propose we jump to something as different as possible. Let's just pick the device that has the lowest fundamental switching energy that we can come up with. So it turns out there's this adiabatic limit, known as the Landauer limit, that says if you change the amount of entropy in the universe by sending 2 bits into a gate and deleting one of them, only one comes out. That costs kBT ln2 energy, basically. So T is the temperature you're at. kBT is related to the thermodynamic system. And okay, so these funny superconducting objects here, we can build parametric amplifiers that are superconducting all the time, and we just use a nonlinear inductance in the superconductor instead of even using resistance. We never even switch it normal, and we can get down to kBT if we want to. And we can build things like adders that actually do relevant math. The second reason you might want to go to superconductor electronics, which is historically why it was investigated for a long time, although it turns out it's a little bit harder to find applications that benefit purely from speed, is that you can set records in the fastest switching technology. So if you want a digital frequency divider, you can make one. It runs at close to a terahertz. If you want to make things like 8-bit adders, you can build those that run at 100 gigahertz plus. In practice, most of the world is limited not by single-threaded speed, it's limited by power, and so I'm going to focus on power. All right, so there's a lot of recent progress over the last 10 years or so that means that it's now possible to build relatively large circuits, whereas 10 years ago it was not, and that's why I'm here now. So if you look at, say, a 90 nanometer CMOS fab, both of these fabs exist within Lincoln Laboratory. Lincoln has the state-of-the-art in superconducting fabrication, where we're building these circuits. You can compare to 90 nanometer CMOS fab. It's a similar stack, similar line widths, similar etch tools, similar depth tools. The main difference is that, number one, we replace our metal wiring layers with niobium, which is a superconductor. Transition temperature is 9 Kelvin. We operate typically at 4 Kelvin, about the boiling point of liquid helium. And we replace our transistors with something else called a Josephson junction, which is essentially a weak link that you can either switch just long enough to emit one magnetic flux quanta to change out of the superconducting state just for a short time. Or my preference is to not switch it at all and just use it as a nonlinear inductor that depends on the amount of current flowing through it. So the moral of the story is that we get to repurpose these older 90 nanometer CMOS fabs. And Dennard scaling never existed for superconductors. It's been long dead. So regardless of the size of the device, the power dissipated is the same. So we don't have to push to 3 nanometers or half a nanometer to get attractive power numbers, which is another benefit. So historically, Dudley Buck invented the cryotron at MIT in the 50s, which is basically an superconducting equivalent of a transistor. You wrap a wire around the superconductor, put enough current through it, and it kills it. So you switch between super and normal. For a long time, there was work on switching superconductors between the normal state and the superconducting domain. You still burn power when you're just a normal metal, and so there's, it's inherently never going to be quite as efficient as being purely in the superconducting domain. And over the past number of years, people have moved to things like qubit-focused processes for simulated annealing, like D-Wave, and we've moved to never switching things out of the superconducting domain as well, even for classical electronics, to get the lowest possible power. We've also pushed in scale, so this is to give you an idea that we can actually build relatively large circuits. So this is a shift register memory. People use these to kind of just benchmark processes and show that there's no dead bits, et cetera. This held the record for quite a while, although I think D-Wave's recent processor is a little bit bigger at this point. It's near 1 million junctions. It's a 1 centimeter by 1 centimeter chip. You can see in the blow-up picture, there's a couple of bit cells there. Each one is 4 Josephson junctions. And it's a 200 kilobit memory cell, so we can build things of large and relevant complexity. And we've been scaling since then, so that was a few years ago, and we continue to scale on a quasi-Moore's law path, although we don't get the benefit of reduced energy. You still want to get to a scale that's large enough that you can fit important things like multi-bit parallel multipliers and adders, max. We want to build a processor that can do something useful. It has to be big enough to have enough throughput to do something useful. And so over the past several years, we've scaled to megabits per centimeter densities, which starts to look relevant to folks who design in CMOS. And you can plot. Wikipedia has a JJ count page that compares us to the Moore's law scaling transistor count page. We started a little bit behind. We're still a little bit behind, but we're trying to jump up the curve as fast as we can. Okay, so now now that you know this thing exists, we can build megabit, per centimeter squared type circuits. We can build big parallel multipliers, et cetera. If you're somebody who wants to design this process, how do you do that in practice? So I'm going to advocate that you use this funny object here, known as a quantum flux parametron. It looks pretty similar to qubit design. There's a couple of Josephson junctions, so those little X's are essentially nonlinear inductors. And it operates, if you've ever seen these old famous papers on adiabatic computation, and there's this beautiful adiabatic model that says, here's the lowest energy way to possibly do math. You take an energy level and you don't just drop from one energy state down to another one. Instead, you slowly move your system to a state where two energy levels exist, to one where only one energy level exists, and back again. And that's literally what we do. So we have this nonlinear inductance, which changes the energy state of the system. And effectively, all you have to know in designing this is that if you put in positive current flowing from top to bottom, you can call that current level 1. When your clock comes, if it's a small positive current, it'll amplitude it up to data level 1. So 1 microamp might come in, 50 microamps will come out. If it's a small negative current, -1 microamp, -2, -5, it's going to get amplified to -50 microamps out. And it does that because of this either change in the energy landscape, you can think of it as, or this kind of saturating nonlinear inductance of the Josephson junctions. And if you want to start building math out of this, you can build majority gates, which just says if you wire a few currents together, maybe it's +1, +1, and -1, two cancel out, +1 wins out, gets amplified back to the data level, and this majority gate is a three input gate, and that plus inverters gets you any logical function you want. So here's a couple of these bit cells and some of our recent work on this library, and so we've designed these gates. You can see at your left the layout, which is a zoomed-in GDS file, which is the same technology used to fabricate CMOS circuits. You can see the schematic. And at my right, your left, you can see memories that are built out of this quantum flux parametron-based circuit, done with collaborators here at CBA on MIT campus. And we stored a bunch of data. And the impressive thing about these is that they may not be as large as the earlier memories, but the bit level energy is about 10 to the negative 21 joules per bit, which is, so this is sort of 24 kBT level energies to store this information. And we started building bigger things. So that was a little 3-bit energy cell, or 3-bit memory cell. And we've recently built up to larger register files, which looks like the level 1 caches that you might see in the stack of a computer core, as well as things like parallel multipliers, adders, et cetera, built out of the same cells. And we have a PDK, we have a cell library, we have a lot of things that we can share to make this easier for digital designers and analog designers in the real world to use them as if they're CMOS elements. So this is not from us, but from some of our friends, one of whom is just down the street at Atlantic Quantum now, who's historically at Yokohama National University, showing that, yes, in fact, you can build full processors out of this that have useful instruction sets and still operate with this few kBT level energy. All right. So the past section is what I would argue is the most relevant application, building low energy processors, scaling these up, tackling this large scale energy problem using a totally different technology. If you wanted to do something different, so occasionally for things like DSP, for example, you want to know, you just want the answer as fast as you can possibly get it. So you might want to figure out, how do I design a circuit that operates digitally at 100 gigahertz? In that case, what you can do is you can actually switch the superconductor. There's a limit to how short of a time you can switch it. It has to be at least one magnetic flux quantum, because magnetic flux is quantized in superconductors. And so you can put a little shunt resistor that lets it switch just for that long, and then it retraps. And then you can take the little pulse you've generated. It looks like a current voltage pulse. It's about 2 millivolts times a picosecond, maybe 2 millivolts high, picosecond wide. And now you can start doing processing at near terahertz. In order to do this, because we only have a 2-terminal device, what you do is you store some information in a local loop, and then you basically sample and check with a clock whether or not there's a 1 or a 0 stored in that loop. And we can work all, I can give the examples for AND gates, OR gates, et cetera, if you care later. But the moral of the story, this is, again, this lets you build everything you want, and it operates at a few hundred gigahertz. So here's an example, 8-bit serial ladder. One reason I say in specific this is relevant to things like DSP and less relevant to things like CPUs is because if you want to operate at about 100 gigahertz, you start to run into this problem that if you have your memory over here and you have your CPU over here, the speed of light, unfortunately, is only so fast, and it's not getting any faster. And so unless you think of a smart way to co-locate these objects, it takes some number of nanoseconds just to get back and forth between the CPU and memory. And so it's essentially impossible in the typical von Neumann sense to operate a CPU at these speeds. People try to do things like pipelining, but that only works even in theory to some number of logical pipeline stages, and it gets slower and slower. So but you can still build things like adders, multipliers, lots of DSP-related problems, including things like matrix math that people care quite a bit about. All right, what next? So my hope with this is to introduce all you folks who might be smart electrical engineers, computer scientists, et cetera, to this unusual technology. It's relatively mature in the fabrication space, but there is an enormous amount of innovation in the computer architecture space, how to encode information, how to process information, what to do with extremely low energy computer processors. And there's significant active work in the design of all of these elements, and it's scaling quickly. So over the past 5-7 years or so, we've brought up this process. We call it SFQ 5E, single flux quantum, EE for energy efficient. And we've had collaborators at many, many places, over 300 publications co-authored using this process. And I hope that perhaps we could encourage some of you to submit as well and help solve some of the interesting problems in this field.
Okay, thank you, Alex. So why don't we take a few questions? Okay, so before we get to some of the questions from the audience, why don't I start with sort of a question from each of you, or for each of you, on what do you see as the top 1 or 2 things that are really holding back to mature the technology that you're working on? I'll start with Ryan.
Sure.
And where's it going? I mean, what is the goal that you see next, and what are the top 1 or 2 things to prevent you from getting?
Yeah, there are a number of, so for Ferroelectric FETs, there are a number of challenges and things that we'll need to continue to do in the development. So this is a new device that's kind of been prototyped. There's still a lot of issues to work out in terms of endurance, reproducibility, and avoiding like kind of killer defects that have all been sorted out on advanced CMOS nodes. But now introducing this new material, you have to kind of go back and understand what are causing some of these new defect modes and circuit failures, and how do we engineer around those. I think there's still questions, what is the actual correct and best gate stack to use? But I think there's a path forward on most of these questions for Ferroelectric FETs.
Okay, so some question to you, Alex.
Yeah, I think for superconductor electronics, so there's a lot of work still in the computer architecture space, and in what's the smartest way to encode information, what's the smartest way to, at the device level, and then at intermediate levels of the hierarchy. One long-standing problem in this field was how to make dense enough memories such that the fab area isn't totally dominated just by memory area, because your logic's very efficient. I personally think we have probably solved these problems, or a couple of things in the pipeline will solve this problem. And the secondary problem is just that hardware development in general takes some time, right? You design a chip that takes you maybe a month or 2 to figure out how to do that and get it to the state that it's clean enough you can go into fab and you're pretty sure that it's going to work if it's a large-scale chip. And then, fabrication takes a few months and testing takes a month or something like that. And so, at this point, we're at the scale of multi-bit parallel multiplies and things like that. And I think, 1 or 2 iterations from then is large-scale processors. So I think we're not too far behind, but that time constant is relevant.
Okay, thanks. Yeah, so let's take one from the audience. Do legacy architectures such as CMOS limit the potential of new materials, such as ferroelectrics? In microelectronics, is there a balance between progressive and disruptive design here?
Right. So, I mean, the way I kind of see this playing out, I think the right approach is to be as disruptive as possible in university settings and in laboratory settings, and the industry will kind of pick out and define the progressive way to integrate them at scale. The good thing about CMOS is, especially at this phase, it is a mature technology. We understand the physics quite well. We understand the architectures quite well. There are many modalities of architectures now. We're maybe integrating new materials on a nanowire device at 18 angstroms is really hard, but if we put this in at 45 nanometer or a 90 nanometer node, we can unlock new capabilities that even those very highly advanced chips don't have. That's one of the approaches. With this ferroelectric FET, it's going to enable new capabilities. This non-volatile memory element doesn't exist in the same way in current CMOS architectures. So it is a new device to be considered in addition to transistors, capacitors, and resistors that we can now build into circuits and think about how, that, in my opinion, progressive change of just adding another element to the gate stack, how that progressive change can actually deliver some disruptive outcomes.
Yeah, so just to dig into that a little bit more, are there examples now of in-memory compute architectures, maybe with a volatile device as opposed to a non-volatile device, that at least the architecture is proven, and are there the expected decrease in energy consumption?
Yes. So the way that kind of in-memory compute circuits are built today is with static random access memory. And it is possible, but it's very power inefficient. There's a huge power draw because you're having to, in parallel, power at least 16 transistors in order to just do one bit of operation in that cell. So if you start multiplying that out and you need to power all of these circuits in parallel, it's something that you can do on a data center scale, something we can't do on any edge device.
Right. So in some sense, the architecture is proven. It's just that the device technology hasn't caught up to the potential for that architecture.
Yeah, I think that's right. That you're marrying an application and a demand to kind of a new way of doing it that's more energy efficient.
Okay, and so now if we pose the same question to Alex. So here, of course, you're wiping the slate clean, so to speak, starting with the new state variable and all the way up. But the computational paradigm that has been matured with the CMOS underpinnings is very powerful. And so yet we don't want to abandon that. So how do we marry this disruption with the goodness of the mature CMOS ecosystem?
Yeah, I think superconductors are exotic enough that it's important to keep the high-level system architecture somewhat similar to CMOS so that people can still, so that the machine code that your C compiler sends is still things like do a multiply, do an add, retrieve something from memory, just to limit the barrier to entry. That being said, the low-level circuits, in many cases are implemented totally differently. Even in this case of a memory, I think a great example is superconductors, because they are quite low loss in data transmission. So if you switch something just long enough to create one single flux quantum pulse, it could go around in circles with quite low loss in a superconducting wire. And so it turns out that delay line memories in superconductors are extremely dense and efficient, whereas they historically actually existed in some of the earliest computers back in the 50s, 60s, using acoustic delay line memories with mercury tubes and things like this. But in superconductors, again, some of these unusual architecture choices that existed back when we had other materials make sense again. to the folks that eventually have to write PyTorch code and run models on these things, that should be abstracted away. But I think there's a lot of room for architectural innovation in superconductors.
Okay, thanks. So how much would the helium supply limit the expansion of superconducting computing? Is there a more readily available high-temperature alternative? We do have some systems that rely on an awful lot of helium. Some of the accelerators, large particle accelerators, rely on superconducting magnets, and there's an awful lot of liquid helium that goes into those systems to cool them down. So I don't know the details on this, but helium is limited resource. And I imagine if we wanted to get to a paradigm where all of our data centers relied on liquid helium, because the most efficient way to cool these systems is actually to embed all of the circuitry in a bath of helium, and then as it boils off, you re-liquefy it. And that's the most efficient way to cool these down. However, there are some closed circuit systems that don't require that liquid helium. And they're a little more efficient.
Yeah. At data center scale, the helium reliquefaction plants that are used for particle accelerators, they're like essentially the same thing, same power draw. Those could be used. That's convenient because somebody already built all this infrastructure. And there's infrastructure for closed cycle helium cryocoolers all the way down to a couple hundred milliwatts of cooling at 4 Kelvin, which is like a rack mount box you can buy from AutoCube.
Yeah,
So right now there are solutions to it, and we're not helium limited. I think even at the scale of a couple of enormous data centers, we would not be limited. This is sort of comparable to particle accelerators. That said, there is additionally a path which looks maybe a little bit more like the Moore's law scaling path. So we don't have Dennard scaling. Smaller devices don't get more efficient. But if we go up in temperature, devices do get more efficient because cryocoolers do worse and worse relative to Carnot or perfect efficiency the colder they get. And so we're working on materials like niobium nitride, folks are working on niobium tinitride, and there's paths potentially to things like, some demos have been done even in YBCO at 77 Kelvin. So there's a path to continue to go to higher and higher temperature superconductors, which also improves our energy efficiency and reduces reliance on things like liquid helium.
Right. Okay, so I don't know that I understand this top question. How can the human computer be applied to next generation computing to prevent excess energy consumption? Is that...
I'm not as good at matrix multiplies in my head as an NVIDIA H100, unfortunately. So maybe, but that's an interesting architectural question. What am I doing that the H100 is not? Maybe we can reframe all the problems and I can just run ChatGPT for you.
Yeah, it is interesting. You look at the image recognition, the speech recognition that we're all capable of. It's pretty impressive if you compare that to the power that's required compared to the H100 from NVIDIA, and we're doing it on like 20 watts. And so I think it is instructive to look to biology and sort out, what's going on here, what's the piece that we're missing in the way that we currently design architectures and circuits. And I think it's very exciting research in neuromorphic computing, dendritic learning. All of these are very interesting pathways. And I think we need creativity. It's attractive to stay in the same line of thinking with CMOS because there's so much industry behind it. But I think the more creative we can be to come up with new ideas on how to actually fabricate novel circuits that may mimic the way our brains work, we might be able to make these energy efficient advances.
Yeah. This is like a little bit out there, but I'll just throw it out for fun. My understanding more or less of why things like biological systems are very efficient is because, all right, in a normal digital system, you have some channel. And, Shannon's channel capacity theorem says if we want to put as much information onto that channel as possible, we should encode digital information, just ones and zeros. But if you want to send the same amount of information with less energy cost, then you can use more symbols. And so you could use like a unary code where you only send a bit once in a while. And it's sort of time bin coded, so that sparse information codes lots of bits at once. And so in big 3D networks, you actually have lots more channel capacity than you need, and so you can very sparsely encode your information. And people, I think, even from the sort of neural network perspective, sort of believe that sparsely connected 3D networks are much more efficient than than densely coded networks or 2D networks. So I think that's sort of where it comes from. It's hard to replicate that in microelectronics. So, but maybe we can think of ways to do it.
Well, so sort of on that theme, question, these two technologies are still rooted in digital computing. Do we think that analog computing will play a role in the future? For example, materials that perform matrix vector multiplications.
So yeah, I can talk to that a little bit. Thing number one is that the most expensive part of this computing is still things like memory access, and it's important to get dense memory as close to your processing to minimize overall, energy cost to talk between these two objects. So it turns out actually in this QFP case, that thing I showed you, this majority gate, we think of it as a 3-input digital majority gate, but if you actually send amplitude-coded data, you can get like a 4-bit multiply accumulate out of that same object for free. The downside of that is, okay, now you have an extremely cheap multiply accumulate, but it's still just as expensive to get data from the memory, and that already costs you 10 times more than doing that bit level single bit majority gate. And so in contrast, I would say where analog coding could potentially be used would be things in, like, for example, delay line memories. Like unary coding is very easy to use in that case, where we decide where are we going to store the pulse and time code that. Right now, we're, again, still limited by density, and so that's not the most efficient way to use it. But if we end up, where we have more channels than we need, that would be another way to push energy for sure.
Yeah. Yeah, so I think just going back to that hierarchical model for computation, that sure, analog computing is interesting. I think it is useful for some class of operations or computations. And there is, as we look higher into that stack, more the so-called domain-specific accelerators, where if you're willing to limit the types of problems you want to solve with your computation system, you can tailor that stack to be very efficient for those. And so there is a lot that we can trade, and doing analog computation is certainly one of those trades. Doing quantum computation is another. But what you're giving up is the generality of what that machine can work on. And the reason the von Neumann has been so successful is that it is so versatile. But as we learn, we need to get beyond that for some of these harder problems that we want to solve.
Yeah, I might add one thing. It's interesting to think, as when I showed that de-lidded Intel chip, and they're already doing multi-tile chips, and this is getting toward that 2.5D integration. This is interesting to think through, as we think about the architectures that are married together through chiplet integration. You could think about having a leading edge chip in the digital form factor, integrating analog compute, RF compute, all in the same platform. And so I think that these various approaches will start integrating together, and it won't be this or that, but we might have many capabilities on one chip, on one package.
Okay. So there was a question. So maybe I'll just pick up from do we think the next generation computing is a startup-friendly sector? Maybe it is tough tech, right? I think that there's certainly some possibilities. It probably needs a few more years of maturation, some kind of a foundry process into what you could design. But there's certainly lots of opportunity in this space, especially the superconducting electronic space, that it has received so little attention compared to what the CMOS architecture or a paradigm has, that there is lots of room for discovery and innovation that I think could revolutionize the field. I don't know if there's anything to
Yeah. From the fab side, superconductor electronics is probably a little bit lower barrier to entry than CMOS, because we're dealing with sort of 90 nanometer fab nodes at this point, and we don't have an energy requirement to push to dense sub-nanometer fab nodes. On the CMOS side, I think there are plenty of people who work on architecture level innovations that tape out to TSMC, et cetera, and that's maybe within the CMOS domain, but in some cases, people have used CMOS processes in somewhat new ways. So.
Yeah, so maybe with that, we'll conclude the session by saying first, we're very pleased to be part of the nano community. Not a lot of people know about us up in Lexington, but we're very accessible, very much want to collaborate with startups, with researchers, with companies. So we have lots of different mechanisms that we can use to do those collaborations. Please, let's engage if you have some ideas in any ways that you can imagine. So, thank you.
Thank you.